All right, so in this video, we're going to be starting to look at multiple regression rather than simple linear regression. And we're going to continue using the MT-CARS data set, but we are going to begin with a manual procedure for finding a model that works well with our data without being overly complex. And then we will look at some automated ways of doing model selection. So to start with, we're going to pull in our data, MT-CARS. In the previous video, we had added some additional elements to our model, and by pulling it back in again, we are essentially resetting it to factory specs, so to speak, and removing all the modifications that we made on it. Now, we're going to, again, recreate our fit for our linear model, but this time we're actually going to start by using all of the variables in the data set. And there's a very easy way to do this. After the tilde, after the MPG, we're just going to put a dot. And what the dot says to the program is use all the other variables except MPG to model MPG. So it makes it very easy to say use everything else. And then we can construct our linear model, and then we can look at the summary. And if we scroll back up a little bit, again, we get a lot of the same information we had before. It reminds us what our model is. We look at our residuals as an overview, and we get a list of coefficients, which is quite long, that includes our intercept, but then also all of the other variables besides MPG that are being used to model MPG. Now, if you look at the p-values for each of our individual coefficients, remember that the null hypothesis here is that the coefficient, the constant in front of that variable is 0, and the alternative is that they're not 0. And actually, if we look at all of these p-values are above 0.05, our standard significance level. Only one of them is below 0.05. Now, only one of them is below 0.1. So does that suggest that we should eliminate all of the variables in the model and only use maybe weight? I don't know. We might be able to come up with a more complex model that does a better job than just weight alone. But right now, we have way too much going on in this model. We are overfitting the data dramatically because we don't need this many variables. And as we saw from looking at the table of correlations, at least some of our variables are highly correlated with each other. And so by including both of them in the model, we're necessarily creating some bad fits. So there is a selection method called backward selection, where what we're going to do is we're going to essentially start with our full model. This is all the variables that are available to us. And then we are going to start eliminating those variables one variable at a time so that we can work backwards until we get down to a point where the variables in our model have p-values that are all below our significance level, so that they're all statistically significant. Now, we don't want to just jump to the end, because every time I remove a variable, if it's collinear with other variables in the model, the p-values are going to change. So I don't want to, again, I don't want to leap forward and eliminate a whole bunch of things at the same time. I want to do this very methodically and eliminate one variable one at a time. Now, one way that I can go about doing this is I can just subtract one variable from my statement. So what I can literally do is I can say, here I want to just use the same full model that I had before, but now I'm going to take off one variable by subtracting. In this case, I'm going to start by subtracting the cylinders variable, because as I look at my list of p-values, this is the one that has the highest p-value. So it is the one that is contributing least to my final model. I can do that. And so if I ran this, that would calculate the coefficients on everything but the cylinder variable. Now, I suspect that I'm actually going to need to eliminate more of the variables. And so in that case, if I keep just subtracting, eventually I'm going to subtract a lot of things. So instead, what I'm going to do, since I'm doing this backward selection, is I'm simply going to write out with plus signs all of the variables that I am currently keeping in my model so that I can eliminate them by just copying and pasting my same function and then just deleting the variable that I no longer need. So it starts out with a little bit more typing, but in the end, it's going to be a little bit easier to just eliminate variables as I go. So this version where I am literally listing out all of the other variables except cylinder is going to be an identical model to the one that I calculated above. So I'm not going to display both of them because they are literally the same thing. But there are two ways to get to this example. You can take the whole thing, minus out the variables you don't want if you're just selectively eliminating a couple of variables, or you can literally list out all of the variables you want to actively include. And so if I run this and then do my summary, and then run that, I can scroll back up. And again, these are my coefficients. And I can see my weight p-value. It's still not quite below 0.05, but it did come down. That's good. In my previous model, my next highest p-value was 0.88 for VS, and that has come down some to 0.84. But basically all of the p-values have come down a little bit, some more than others, but certainly at least a little bit. So again, I don't have a model where all of the coefficients for all of my variables are statistically significant. And so again, if I'm doing this manually, my goal then is to try this again and eliminate one more variable and then just keep going, starting with the highest p-value, and then each time reassess, delete one more variable with the highest p-value until I can get all of my coefficients with p-values below my significance level, whatever it is that I've set for my problem. I'm going to go with 0.05 since that is the standard significance level. So I'm going to do this again. The variable that I want to eliminate is VS. So I'm just going to eliminate that, and then we'll run this and look at the new model. And let's go back up here. Again, the weight coefficient, the lowest one, it came down again. But I don't have everything below statistical significance yet. So the next highest p-value appears to be for carb. So that's the next variable I'm going to eliminate. And again, this is basically manually doing backward selection. My weight has come down way below 0.05 by eliminating that variable. And I have another one, the Q second has come down also below 0.05, so we're making progress. Let's see, what is my next highest p-value? It's going to be gear. So we're going to continue eliminating. All right, so good, good. These are still good. This one is getting closer. My next highest p-value that's still above significance is going to be this guy. So I'm going to eliminate that one as well. And we're going to run that. We've got another one below 0.05. That's fantastic. I still have three, my intercept and two more variables that are above 0.05. So the next one I eliminate is the displacement. And then again, one variable at a time, because as you can see, each time I eliminate something, the p-values for the other variables will change. And in this case, my Q second one actually came up when I eliminated that, which isn't great. But my HP, my horsepower variable is still much too high. So that will be the next one we eliminate. And it looks like our three coefficients, we have three variables left in the problem. Those p-values all look still very good. The one that we have still that's a problem is the intercept. And so the way that we are going to reduce the intercept we saw in the previous videos, we're going to add a +0, and then that will force the constant to be 0. And so when we run that, we have a equation for MPG, which depends on three variables: weight, the time in seconds to a quarter mile for acceleration, and the automatic versus manual variable. And we can see these are all quite low. Some of them are extremely, extremely low, but they're all not only lower than 0.05, they're even actually all lower than 0.001, which is fantastic. So these are all really good. And we can see our multiple R squared is now 0.987, which is fantastic. Our residual standard error is another thing that we can look at as we eliminate variables to see if our residual standard error is getting smaller, or maybe not necessarily getting smaller, but not changing very much. And then, of course, our p-value for our full model no longer matches any one of our coefficients because it's looking at the entire model. It's basically saying all of the coefficients in the model are 0 versus, as the null hypothesis, versus at least one of them is non-zero. And here, we have at least 3 coefficients that are non-zero. So this would be our model equation, and then we could do our traditional analyses that we saw. We could, for instance, look at the residuals. Again, we would want to plot the residuals against each of our 3 variables, the residuals versus the weight, the residual versus the Q second, and the residual versus the AM variable. Now, the AM variable is a discrete variable, so the scatter plot will look a little weird because you'll have only all the data in 2 columns. That's not necessarily bad. It's just that's what discrete variables end up looking like. But you do want to check for things like the spread and make sure that the spread is not dramatically different on, say, 0 versus 1 or something like that. Given the p-values, I don't think it's going to be that big of a problem. Now, this was doing this backward selection process manually. You can get R to automate some of the steps. Now, when you use the automated version of this, it is not necessarily going to use the p-values for the coefficients as the cutoff value. It's actually going to use a different value for the cutoff. And so you may end up with a model which is the same as this, or you may end up with a model that has some additional variables in it that actually don't quite meet our the traditional requirements for the statistical significance of the coefficient hypothesis tests. So let's check this out. So we're going to use a function from the mass package. And again, if you have never used this before, make sure that you install it first. And then we are going to, in this case, we're going to start with the full model again. So I'm going to go back to the top here. And I'm going to use 2 just to preserve my final model from our manual backward selection. And again, we can look at the summary that we looked at earlier with all of our coefficients back in the model. So this is what we had earlier. Now, what we can actually do then at this point is we can have the mass package eliminate some of our variables for us. So this function is called stepAIC. The AIC is a information criteria that this function uses to eliminate variables. It's essentially looking for the smallest AIC value. The AIC is something that we'll talk about in another one of these tutorials, but essentially it is another way of looking at the quality of the fit of our model. It just uses a slightly different calculation than some of the other things that we've been using, like the residual standard error or the p-values. So in this case, the direction both, so you can do backwards, or you can do forward, or you can do both. Let's actually just try backwards first so that we can compare it to our backward selection, and then we will do both in order to see if we get the same answer. The forward process would be to start with like your best correlated variable, which I think would be weight. If we remember the correlation table from a previous video, and then you would start adding on additional variables, and you would keep things in the model where the p-value remained below the significance, and you would remove something if you put it in and the significance failed. Then you would pull it back out and you would try a different variable. So that's the forward selection where you're building up from the smallest model with one variable, trying to add things in. The backward selection, you start with a full model and you try to remove things until you get to a good model. In this option, when you do both, they're actually going to run through the forward process and the backward process to try to get this lowest AIC value. But let's just try to run it backwards to start with, since that's what we were doing manually. And then we can get a summary. And in this case, the backward selection model actually came up with the exact same model that we came up with. Let's try the forward model, see what the forward model comes up with. Now, some of these processes, they are going to depend on the order that you add the variables in, particularly for the forward one, because you may add them in a slightly different order and get a slightly different result. In this case, we got the same model, and so I would imagine that if we did both, that we also end up with the same model. Now, this does happen sometimes where you will end up with one optimal model that this function will find, but be aware that this is going to depend on the data set. I have run it on other packages, other data sets, and sometimes I get the same model, sometimes I get the same variables, but I get one additional one in the step model. Instead of only, say, 3 variables, I get 4 variables or something like that. So it is going to depend on the data set, and you will see some variation in the way that this plays out. Now, another way that we can select our best model is with a process called best subsets selection. And so we're going to pull this out of the LEAPS package. Again, make sure that you run this, install this from the tools menu before you try to run this package. And here, what we're going to do, the best subset method is essentially it's going to look at every combination of variables of a particular number of variables. It's going to look at all of the possible subsets and then try to choose from those which one has, again, the best, usually the best AIC is how some of these packages work. You may be able to, if you look at the documentation, use other stopping criteria. Now, the NV max is the number of variables to be considered, the maximum number of variables to be considered in the model. We have quite a lot of variables. I believe we have 10 of them, 11 variables. So we're modeling MPG with the other 10 variables. So I have said, okay, NV max. So there's only one possible 10 variable model. I could restrict this to the best 3 variable model or the best 5 variable model, but it will, if you specify the maximum, it will test all of the models that are smaller than that as well. And then you can then pick the size model that you want to consider, and then it will specify which of the combinations of 3 or 4 or 5 or however many variables you want give you the best combination of lowest AIC or lowest residual error, or whatever its criteria is. Now, we're going to run this, and then we're going to look at the best 3 variable model and see if our coefficients, if the variables that they selected agree. So I'm going to run this now. There's a lot of different versions of this because there's only one top possible model with 10 variables, but there are 10 models with 9 variables, and there's 10 models with only 1 variable, and there's 10 choose 2 number of combinations of 2 variables, and there's a lot of different models to test. And so this may take a moment when you run this. Again, it depends on, there's only 32 observations, so it's not like a huge data set, but it ran all the possible combinations. You would not want to do this by hand. But then we can summarize the results. And so what it does is displays a table, and they give a little asterisk for the variables that are included in the model in its best model of that various particular size. So we saw from the correlation that, from the correlation table, that weight had the highest correlation with MPG. So the fact that the 1 variable model uses weight that is the best, that seems straightforward. If we go down to our 10 variable model, obviously everything is checked off because there's only 10 variables in the data set. And if you go to the 9 variable model, you can see that this does agree with our 9 variable model because the first variable we eliminated was cylinders. So you can kind of see the process. Now, the best subsets regression process is not necessarily a backward selection because they will literally test all the combinations. And so there may be a combination of variables that we would not arrive at from backward selection or forward selection for that matter, but that still turns out to have a slightly better model fit than we would get from that sequential process we were following. But if we look at the 3 variable case, we are including weight, Q second, and AM. And so the model that has those 3 variables in it is the same best model that we found by doing our backward selection. Now, if we were to choose one that had, let's say, 4 variables, the HP was the last variable, I believe, that we eliminated. Yes, it was, before the intercept. And so we could, again, look at this and see if we wanted to keep it or if not. This best subsets regression does not test the intercept. So we would then have to test the intercept ourselves. We could run a traditional 3-variable model, for instance, with our 3 variables, and then again, decide whether we wanted to force the intercept to be 0 or not. But this is another way of getting the regression, and it may or may not agree with our analysis from our other methods of choosing our best model. Now, once we have chosen our best model, and we have, again, if we pick different combinations of variables from our table here, we would then go back and rerun our linear model with those variables. We then still have to do various diagnostics. So one way that we can do this analysis is to look at our a package called ENV stats. It stands for environmental statistics. It has some outlier tests in there, such as the Rosner test, that we can use to see if any of our variables have outliers in the residuals. So I'm going to load this package. And again, if you have never used it before, you will need to install it under Tools. And then we are going to we're going to create our residual column. As we did before, using the residuals and our fit model. That was the best model that we got that agreed with all of our other processes. And then we're going to do our Rosner test. And in the Rosner test, we're going to put our MT-cars residuals. And I'm going to test this for k equals 3. The nice thing that I like about the Rosner test is it tests to see whether or not our values are outliers, and you can specify the number of outliers you want it to check. So if you've looked at the fit and you've looked at to see if any of the residuals are potentially problematic, you can, for example, just specify, okay, I think there might be 3 outliers. Let's check them all. You don't have to do one at a time as you do with some other kinds of outlier tests. We could actually create our plot for the normal probability plot for our residuals so that we can see if there are any or how many there might be. So if you recall from the last video, which equals 2, and I'm just going to go ahead and plot that without worrying about the color. And so there are some potential ones out here. And so I'm going to test to see the 3 most remote outliers. Are they outliers or not, the largest residuals? And what the test says is it basically tests each one. And if it is identifiable as an outlier according to this test, then it will say true. And if it's not an outlier, it will say false. And it will test them in sequence. So typically, if the first one is not an outlier, they'll all come back as false. But if the first one is an outlier, it will remove it from the data set and then retest. And it also is very nice in specifying the observation numbers that are potentially problematic. So this, we may not be able to tell from this graph which of the observations, because they gave the names of the vehicles, not the observation numbers. The Rosner test will list the names of the observations. So in fact, if you do choose to remove some of the potential outliers, you know which observations were the potentially problematic ones. So that's great. We can also use a package called 3D scatter plot if we want to look at multiple variables and how they relate to a third variable. So when we plot a 2D scatter plot, we have one variable plotting against the second variable. But if I want to plot two variables against the third variable, I need to go into 3 dimensions. And so I can go to 3 dimensions. I can't go to 4 dimensions. I can't visualize 4 dimensions. Again, this is another package that you will need to make sure that you load before you attempt to use anything out of it. So this is our scatterplot 3D package, and we're going to create scatterplot 3D for this is a package. It's a data set, trees, that I think is again, it's built into R already, so you can just call it. And there are 3 variables in the data set. We have girth, height, and volume. And so you can see that it's plotted this graph in 3 dimensions. Now, because this graph doesn't rotate, there are ways that you can actually specify the rotation if you look into the package documentation, so that you can look at it from different perspectives. This one does not move very easily, but there are other packages that will allow you to interact a little bit more with the graph. And one of those packages is Plotly. And so we're going to manipulate this data set just a little bit, our MT cars data set, so that things will graph a little bit more nicely for us. So MT cars, our automatic versus manual variable. When that variable is equal to 0, we're going to call that automatic. And I need to spell my data set correctly. And when it's equal to 1, I'm going to replace that with manual. And I'm going to make sure that it is registered as a factor variable. That's just going to make it easier to plot. Because it is a discrete categorical variable, I can actually plot it in 3 dimensions against my other 3 variables by using color to represent my categories. So the Plotly syntax works quite a bit differently than the ggplot syntax. So you do have to get a little bit used to it before using it. Again, the syntax is just a little weird, honestly. Now I'm not choosing the 3 variables that are in my model. In this case, I'm predicting the quarter second time using horsepower and weight. And then I'm going to color code it with the AM variable. And again, feel free to play around with this and try to use the variables in your model to see how that works against MPG. Now, if I want to specify colors in Plotly, I need to do them with hex codes. Especially if I'm picking anything that's weird. Now, the nice thing about the latest version of R is that it will tell you, it'll display what these codes turn out to be as soon as you finish typing them. So that you can see what the colors look like. And then I'm going to and we're going to pipe stuff through here. And we're going to add markers. And then furthermore, we're going to also add a layout. This is our weight variable, and that needs to be in quotes. Hopefully I don't have any glaring typing errors. And then we can print it. So let's see how we do. I loaded package, so let's run this. And here's our graph. Now, Plotly, the nice thing about Plotly is that it is interactive. And so you can rotate the graph in order to see things from different perspectives. So that is nice. Now, again, we changed the AM variable. That's color coding everything, automatic versus manual. You can see there is sort of a difference in the relationship here. Our gross horsepower is on this axis. The weight is on this one. The 1/4 mile time is here. And the other nice thing about Plotly is that if you hover over the coordinates, it will tell you what the coordinates are of those points. You can also add other kinds of notation to these graphs so that you can actually get more information out of these graphs than what is there to start with. And so if you're looking for different perspectives, this interactivity, again, is going to allow you to actually see more of the 3D, and you can rotate it until you get it in a position that you like it, and then you can just screenshot or save it. You can actually also export this to something like a web page or something like that so that you can access that interactivity outside of the viewer option here. And if you hit zoom, then it will pop up into a larger window. And again, you have more options for rotating and getting some of that additional perspective out of the graph. So it can be really nice for playing around with and experimenting with your data. And again, the interactivity is fantastic compared to a more static graph where it is much more difficult to see that three-dimensional perspective.